Hi kids, this is Miss Nichols and this is video 13, which is on conservation of momentum. So we've already learned about conservation principles, and this is how to apply them specifically to a new variable called momentum. The essential question is, what is momentum and how do we use conservation of momentum to make predictions about objects in a system? So momentum is a new variable for this unit. This may be a word you've heard before or maybe not, and you probably have a sense, if you have heard it before, about what it means to have a lot of momentum, but we're going to learn about what it means as far as physics goes. First thing you should know that momentum's variable symbol is actually p. So even though the word starts with m, we don't use an m for momentum, probably because we already used up m on mass. So the variable for momentum, even though it sounds funny, is p. Momentum could be defined several different ways. The technical term is, or the technical definition would be the product of an object's mass and its velocity. So you should have a sense that the size of the object and how fast it's moving are what are going to contribute to its momentum. But kind of an easier way of thinking about it, for me at least, is that objects with a lot of momentum are harder to bring to a stop. So if you picture yourself physically trying to stop an object, something with a lot of momentum it's going to be hard to stop, and something with a little momentum will be easy to stop. Momentum could be a positive or a negative value, like velocity that we learned about in the last unit, or delta D, displacement, could be positive or negative. And the sign of the momentum will tell you which direction the object's moving, just like with velocity. So if you are moving in the positive direction, then you're going to have positive momentum and positive velocity. If you're moving in the negative direction, it's going to be negative, both of those. And just like with velocity, if you are at rest or you're standing still, you've got zero velocity, you're also going to have zero momentum, which should kind of make sense because it would not be very hard to bring that object to a stop because it's already stopped. The units for momentum are sort of challenging ones. They are kilogram meters every second, so it's a kilogram times a meter every second, and there's no real shortcut for that. We just have to write that whole thing out. But that's the typical unit for momentum in this class. So we're going to spend a few slides deriving the relationships that make up the momentum equation. And I think that this should be pretty logical to you guys when you think about objects and how hard it would be to bring them to a stop. So for example, which of these two objects do you think it would be harder to stop? This is the world female cycling speed record holder, and her mass is about 95 kilograms, and the fastest clocked speed that she ever went was 147 miles per hour, which is crazy fast. So would it be harder to bring her to a stop, or this is a Bugatti Veyron, which is an amazingly fast sports car. It can also go 147 miles every hour, and it has a mass of 1,990 kilograms. So obviously they're both going to be tough to bring to a stop, but who would be easier, the cyclist or the Bugatti? Hopefully, if you think about it, you realize that the Bugatti must have a lot more momentum. It's going to be much harder to bring to a stop. And the reason it has so much more momentum is because its mass is much larger. So in other words, mass has to have a linear relationship with momentum. The bigger the mass, the bigger the momentum. There is one more variable that contributes to momentum. By way of an example, which of these two objects do you think would be harder to bring to a stop? The first one is a football player, Jerome Bettis, and he's walking towards you. He's got a mass of 120 kilograms, and he's walking at a velocity of 1 meter per second. So imagine trying to bring him to a stop as he was walking towards you. And then compare that to how hard it would be to bring him to a stop while he's running towards you. Same mass, 120 kilogram Jerome Bettis, but this time he's running at 9 meters per second. So which one of those two football players would be harder to bring to a stop? Probably pretty obvious to you. The second Jerome Bettis, the running one, would be harder to bring to a stop because he has a much higher velocity. So the bigger the velocity, the bigger the momentum, which means there is also a linear relationship between velocity and momentum. So if those are the only two variables that matter, mass and velocity, we can combine those two relationships into an equation. So we know that momentum has got a linear relationship with mass, and it has a linear relationship with velocity, or v. Think back to the last unit when we talked about deriving equations, and I would really recommend pausing this slideshow here and seeing if you can come up with an equation for P given those two relationships. Hopefully you came up with something. The equation for momentum is just the product of the mass and the velocity. It's two linear relationships, so they're both going to be on the top or the numerator of the fraction of the other side. So P is equal to m times v. Before we talk about how we use conservation of momentum in systems, I want to just take a little bit of a second and just talk about types of objects in the real world that we would see and how much momentum they have. So I made a table of mass on the kind of top column labels and velocities on the row labels. And I would fill in each of those boxes with an object that you think would fit there. So an object that has a large mass and a large velocity would go in the first square, small mass and small velocity in the second square. I'd recommend pausing the video and filling out your own table so that you have your own objects that make sense to you, and then coming back and I'll talk to you about the ones that I picked in just a second. Hopefully you filled out your own table. So the example I came up with for a large mass and a large velocity would be an airplane flying. Note that I have to have the object and something about its movement. So an airplane sitting at rest is a different momentum situation, so I needed to include that flying piece. Small mass, large velocity, I chose a flying bullet, which is, I think, a common one people think about. Large mass and a small velocity, I mentioned an elephant walking. Small mass and small velocity, a beetle crawling. An object that has a large mass and no velocity is the universe. I know that sounds funny because things in the universe are moving, but the center of the universe is not moving. It's expanding. The whole size of the universe is changing, but the very center of it is not moving. So we actually know that our universe overall has no velocity. And of course, compare that to something with a small mass, also with zero velocity, like a tiny rock that's sitting on the street. So the reason I color-coded these is because it should be clear that some of these objects have way more momentum than others. So in the high momentum category, I would say that airplane has the most momentum of any of the objects I listed on this table. High momentum. The bullet and the elephant are going to fall somewhere in the medium momentum category, and then low momentum would be the beetle crawling, so way less than the bullet or the elephant. Those last two, the universe and the pebble at rest, even though they're really different feeling objects, they both actually have exactly the same amount of momentum, which is none. So every object at rest in the universe or the universe itself actually has no momentum. And it makes sense when you calculate it out with that equation too, because if the v is 0, then any number times that v is going to be 0 as well. So we would use conservation principles together with momentum to analyze objects in systems. Sometimes we're going to put them in closed systems, and sometimes it makes more sense to have an open system. An example of when you might use conservation of momentum in a closed system, something like a game of pool or billiards. I don't know if you've all played that, but you've probably all seen pool balls before. And if you imagine a closed system containing all those pool balls plus that one white pool ball that's already been hit, okay, so that pool ball is already moving, that could be considered a closed system. And the momentum in that system is going to be the same whether we're talking about 1 second ago or we're talking about, right now, basically, right after that, that white ball hits all the rest of the balls. So that means we've got to have the same total momentum in that system, or sigma p in these systems, at any time, whether it's before that ball hits or after. Mathematically, you might be able to calculate that the momentum of that white ball before it hits is 10, positive 10 kilograms meters per second, or meters every second of momentum. And then we've got 15 more balls that are sitting there with no momentum because they're at rest. And you can just add up all the momentum of every object in the system. You've got 10 plus 0 plus 0 plus 0 plus 0, whatever, 15 times. You can figure out that 1 second ago, the sigma p, or the total momentum in the system, was positive 10. All of that momentum was in that ball, that one white ball. And so that's the whole momentum for the whole system. It obviously looks a lot more complicated when you look at what the balls are doing after it gets hit. But you could measure the masses and the velocity of all of those balls, and you could write it down. Some of them are going to have positive momentum, plus 30, plus 20, plus 20, etc. And some of them might be at rest. That black ball in the middle and the yellow ball look like maybe they might be just at rest after they get hit anyways. And some of the balls are going to be moving in the negative direction and would have negative momentum. But conservation of momentum tells us that if you add up all of those momentums, and you're welcome to do it if you would like, you are going to get the same sigma p, positive 10 kilograms meters per second, when you are done as that system had before. So the total momentum had to stay in the system. It might look really different because different balls have different amounts, but we're going to have the same total amount in the system. We could also use conservation of momentum to talk about what happens in an open system as far as momentum goes. So, for example, an open system containing a soccer ball, it might make more sense to talk about this as open because there's lots of different forces and factors that affect the velocity of that ball. It's going to be changing momentum pretty rapidly. So whatever the soccer ball does when it starts, things can change it. Like, for example, a person might come and kick that soccer ball and add some momentum to that ball. So when I kick that ball, I add 60 kilograms meters every second of momentum. Of course, if you wait a few seconds, that soccer ball might start to lose its momentum due to rubbing on the ground. So maybe it's lost another negative 20 kilograms meters every second of momentum just from rolling on the ground. So this soccer ball, instead of talking about sigma p for the system, because the total momentum in the system is changing as momentum comes in and goes out, but we could talk about the delta p in this system, or the overall change in momentum of this soccer ball. So no matter what the soccer ball started with, we know that it's gaining 60 kilograms meters per second from the person, and it's also losing 20 kilograms meters every second of momentum from rubbing. So we could know that the overall delta P for this ball is positive 40 kilograms meters every second of momentum. So no matter what it started with, what we do know is that it changed by a certain amount. One note about this, even though that 40 kilograms meters a second of momentum was added to the ball, okay, it didn't just generate out of nowhere, right? Some other system had to lose that much momentum, exactly that much momentum, since momentum's conserved in the universe. So probably the person lost some momentum, the ground might have gained some momentum, but if the ball gained a certain amount, something else in the universe lost it, because it is a law of conservation that the total momentum in the universe is going to be conserved. All right, let's revisit the essential question from the beginning. What is momentum, and how do we use conservation to make predictions about objects in a system? And when you've written your summary, go ahead and click over to that quiz and see how you do on those questions. Thanks a lot.